Hello, everybody, once again. So it has come down to the last lab lecture, talking about the last lab experience. Next week at this time, we will be having the lab quiz, which is going to be 20 or 25, something like that, multiple choice questions about the lab experiences that we've had. I'll be publishing a study guide because I don't want you to think that, well, what in the world is he going to ask us about? So I'll be publishing a study guide to coach you up for the lab quiz, which will happen next week at this time. And, you know, it'll be the same protocol that we're following for everything else, that will release the lab quiz at a certain time, probably 11:30. And then it will be due in an hour. It's multiple choice. I'll be publishing a study guide to help coach you up for what you're supposed to be looking for. All right. So last experiment, experiment number 6. Experiment number 6, which is about the synthesis of nerolin. Nerolin is a perfume fixative. So it has a mild aroma of its own, but it's usually used in personal care products to help support the more aromatic principles that might be in there. So, you know, the cologne and the perfume, they stick to the nerolin sticks to your skin. And so it's a perfume stabilizer and fixative. Okay, so the synthesis of nerolin will involve taking this 2-naphthol. This is called 2-naphthol, and reacting it with a base, potassium hydroxide. The solvent here is methanol. And the OH proton of 2-naphthol is acidic. It will be removed by OH minus, which maybe you remember from Gen Chem is a base. And so we have this acid-base reaction in which the OH proton of the nerolin is removed, and we get this naphthoxide plus water. Okay, so where did the water come from? Water used, the H plus, the proton that was removed from naphthol, got together with the OH minus to make water. Okay, and then the 2-naphthol anion, this guy, interacts with iodomethane. And once again, our solvent is methanol. Methanol solvent. And the O minus displaces the I of iodomethane. And so this is the nerolin. Okay, so I have a couple of things. I have quite a lot to say about this reaction. First of all, talk about some of the practicalities of this experiment, and then talk about some of the chemistry. Is that in this experiment, we will be using we're going to be cooking the reaction in a microwave oven. use microwaves for heating instead of a situation in which we would be mixing the reagents and putting them in a like a glass vessel and putting them on a hot plate or over a Bunsen burner or something like that. Instead, we're going to be using microwaves. And so if we were doing this experiment for real, what we would be using is this microwave tube, and this is where the reaction mixture would go in. And this microwave tube, this is what goes into the microwave oven. It's made out of Teflon, and that turns out to be a very important design feature. You know, if you just like at home, when you want to heat up some soup or something like that, you can do it one of two ways. You can heat up your soup conventionally. You put it in a pan, you put the pan on the stove, you turn on the gas or the electricity or whatever. That's conventional heating. Another way you could heat up your soup would be to put the soup in a bowl, put it in the microwave oven, press a button, and in a couple of minutes, you get the same effect that you would get by maybe having to heat conventionally for 10 or 15 minutes. So the microwaves are much more efficient at heating stuff than a conventional heat source. And this turns out to be one of the features of this synthesis of nerolin, because when you think of conventional heating, most of the heat, you put your pan on top of the stove, you turn on the gas, most of the heat goes into heating the air around the pan, right? The kitchen gets hot. No one wants to bake bread on a day where it's 100 degrees because the kitchen gets hot. Most of the heat in conventional heating goes into the air. Where else does a lot of heat go? A lot of heat goes into heating the pan, right? You're not going to eat a pan, you want to eat the soup. And only a small fraction of heat is actually invested into heating the soup. The situation is totally different with the microwave, because in microwave heating, yes, the reaction vessel is in the air, but air doesn't absorb microwave radiation. So none of the microwaves are going in to heat up the air. The solution is in a microwave tube. The tube is made out of Teflon, but the Teflon doesn't absorb microwave radiation either. So that all of the microwave radiation, all of the heat is going into heating the reaction mixture, and very little of the heat is wasted by heating the surroundings, the environment around the reaction mixture. So that's why if we did this experiment with conventional heating, we would have to boil the reaction mixture for about an hour. But using microwaves, the reaction is all over and done with in 10 minutes. So, the same kind of enhancement that we would see in the kitchen is also offered. That same enhancement is also conferred by microwave heating in the laboratory. Okay, so that's one of the features of this experiment, is that you're using a microwave. And I think maybe the teaching fellows will show you a picture of the microwave and maybe describe how it works. Okay, so that's one of the practicalities of this experiment, is that we're using microwaves instead of conventional heating. So now let's talk about some of the chemistry of the experiment. First of all, step number one is an acid-base reaction, where you take the 2-naphthol and react that with Okay, this is the acid, right? And you react that with hydroxide ion. This is the base. And maybe you remember from Gen Chem that an acid is a proton donor, a base is a proton acceptor. So what is happening here is that the acid gives up that proton to the base. And so you get this naphthoxide plus what looks like water. So that's just the acid-base reaction. But there's a whole lot of chemistry, behind the scenes chemistry, that is going on here as well. Because although this guy is an acid, there's organic molecules exhibit a wide degree of acid and base strength. So just like water is an acid, but so is sulfuric acid. Sulfuric acid is a much stronger acid than water. So we'd like to say a few comments about the acidity of naphthol. But because this molecule takes a long time to write, let's look at something that is a little bit simpler and a little bit more efficient that gets the point across, which is something like this. Phenol, right? This is phenol, is a much stronger acid than cyclohexanol. So this isn't, okay, this is cyclohexanol. So you're not going to be using phenol in this experiment, but this is a nice model compound with which to discuss the acid strength of the 2-naphthol, which you're actually going to be using. So this guy, phenol, is about 10 million times more acidic than cyclohexanol. And so we would like to explain why something like this would be acidic in the first place. Okay, and the reason for that is that when the OH group is bonded to a benzene ring, either in naphthol or in phenol, when the OH group is bonded to a benzene ring, the base comes along, it removes the proton, and we get ionization of the naphthol to give this. Okay, and so this is just a simplified, dumbed down version of that, right? I'm talking about why phenol would be an acid and why 2-naphthol, what's actually used in the nerolin experiment, would be an acid in the first place anyway. Okay, so this guy, maybe we see, oh, we could draw all kinds of resonance structures for a compound where you have an O- attached to a benzene ring or to something fancier as it is in naphthol. So we can draw all kinds of resonance structures. So that would be one. Could draw another resonance structure. That would be another one. And then we could draw a final resonance structure, which would look like that. And we see that, and we know that the actual structure of the molecule is a composite of all of its resonance structures. So that this ion, the resonance hybrid, the actual structure would be, well, none of these bonds are really single bonds. None of those bonds are really double bonds. They're all somewhere in between being double bonded, single bonds. So I'm representing that by that dashed line. And this bond to oxygen, he's not really a single bond. He's somewhere in between being a double bond and a single bond. Okay, and now what about the charges? Well, this oxygen has a partial negative, and then you have partial negatives on 3 carbons in the ring. So that the negative charge is distributed over the whole molecule. Okay, so that's what happens when you are mixing a base with an OH group that is bonded to a benzene ring. So this is a strong acid. Versus something like cyclohexanol, where when you mix that with a base, you're going to get water. The base is going to remove the proton. You're going to get this. And now we try to draw resonance structures. There aren't any, no resonance structures. So that this negative charge here is stuck there. Okay, so now we've said that this is a stronger acid. We've said that this is a weaker acid, and by a lot, 10 million times weaker acid than this is. And so we understand now, looking at these resonance structures, why that is so. Because removal of a proton from phenol or from naphthol, which is what is used in the nerolin experiment, removal of a proton from phenol gives you something that is resonance stabilized. And molecules want to be resonance stabilized. They enjoy the stabilization that is conferred by resonance. The energy comes down. This guy has no resonance structures and no resonance stabilization. So why would this proton want to leave in the first place? When it leaves, it's just going to generate something that is high energy and not stabilized. When this proton goes away, it's going to give you something that is resonance stabilized, that is enjoying the delocalization of that negative charge. Negative charge on this cyclohexanol base is stuck on that oxygen atom. Whereas here it's all distributed around the whole molecule. That's a much more stabilized situation. Okay, so in the synthesis of nerolin, the first step is the formation of this anion with the O- on the negative charge. And so that can be accomplished easily by adding sodium hydroxide. If we added sodium hydroxide to this, we wouldn't get much of a reaction because this proton in cyclohexanol doesn't want to go away. Because when it does, you get something that isn't stabilized versus the situation up there with the naphthol or with the phenol. Okay, so that's the first step, which is the formation of this O-. And the next step is going to be the displacement of iodide by that naphthoxide anion. So the second step is what is called, an SN2 reaction. Okay, and we don't need to worry about why it is called that. Let's just explain what it is and not bother about explaining the name. Okay, in the second step, what happens is that naphthoxide reacts with the ethyl iodide. Okay. But before we show what happens in more detail, let's talk about this ethyl iodide, or 1-iodoethane. That's the official name. Let's talk about this a little bit. Who's more electronegative, carbon or iodine is? Who's more electronegative, carbons or the halogens? Well, I hope we know by now that halogens tend to be more electronegative than carbon. So this carbon-iodine bond is polarized away from carbon and toward iodine. Iodine's more electronegative than carbon. Iodine is sucking electrons away from that carbon atom. So that if we wanted to show that, we would say, or we could write that this carbon atom is partially positively charged, whereas this iodine atom is partially negatively charged. And so what we're just saying here is that iodine's more electronegative than carbon. The halides are more electronegative than carbon. And so it's just sucking electrons away from that carbon atom. The electrons are ganging up near the iodine. Okay, we have a great setup here now because positive loves negative, right? We have this negative charge on this oxygen atom. We have a partial positive charge on this carbon atom. And so what happens in the second step of the nerolin synthesis is the attack of the negative charge on the oxygen on the partial positive charge of the carbon. I'm representing that attack with this arrow, showing the motion of an electron pair. But we can't stop there, because if we just hook up that oxygen atom to that carbon atom, what we're going to get is a carbon atom with 5 bonds. So something's got to snap. And what snaps is the carbon iodine bond. The iodine is hungry for electrons. It's greedy for electrons because it's electronegative. And that's what electronegativity is, a greed for electrons. So when the O- comes in, the carbon iodine bond breaks, and that iodide, I- is going to be a free swimming entity. Okay, but before we picture all of that, how about let's picture the transition state for this reaction. Remember, the transition state, that is something that lives for about 10 to the minus 14 seconds. And what it is attempting to convey is the process of bond making and bond breaking. So this oxygen atom is making a bond to that carbon atom. And I'm representing that bond that is in the process of being formed by this dotted line. And the carbon iodine bond, he's snapping. He's about to break off. That iodine is going to be a free swimming entity in a minute. And when this SN2 reaction is over, what has happened is that the oxygen atom has replaced the iodine. Oops, I drew too many carbons. Sorry about that. This should be CH3 up here, right? That's ethane. CH3 there. So that's the nerolin. And the iodine has departed the scene with this negative charge. Okay, so let's revisit the transition state and see we have to clean something up. See, this oxygen atom came into the reaction with a negative charge. At the end of the reaction, it's neutral. So that at the transition state, the negative charge on the oxygen is going away. It starts negative, it's going to end up neutral. So that at the transition state, the oxygen atom bears a partial negative charge. Okay, now let's look at this iodine atom. This iodine atom starts life neutral. There's a partial negative charge, but formally it's neutral. And at the end of the reaction, that iodine atom pops out with a negative charge. So at the transition state, this iodine atom still has this partial negative charge. Okay, so that's the structure of the transition state, showing bonds in the process of being formed and bonds in the process of being broken. And the charges make sense because The reactants have an overall negative charge. The products have an overall negative charge. The transition state has two partial negative charges adding up to a full negative charge. So the negative charges make sense. It's just an illustration of charge conservation. Now, this kind of reaction turns out to be pretty general, and we have lots and lots of different examples where we would have an O- attacking something that has a carbon atom bonded to a halogen. And so this kind of reaction, this is a specific example of something that is called the Williamson ether synthesis. The Williamson ether synthesis. So our synthesis of nerolin is an example of the Williamson ether synthesis. Okay, so here we start out with an alcohol, right? But this alcohol can also be bonded to an arene. So I'm going to represent it that way. So that R can be alkyl or it can be an arene. And we react that with some kind of base. Right? You're going to use hydroxide in this experiment, but there are many other bases, so we use some kind of base. And the base removes that proton from the alcohol or from the phenol, and we end up with this alkoxide or phenoxide ion. Okay, that's step one. And then in step two, we add a alkyl halide. I'm going to call it that. And the O- comes in, kicks out the halogen. This is that SN2 reaction. And our final product here is an ether, right? So just hundreds or thousands of examples of this reaction could be adduced, right? This is one way of making an ether. So let's look at some examples that are not the reaction that you're going to be looking at in this lab, but are Williamson ether syntheses anyway. So for example, I could take propanol, react that with some kind of base, maybe sodium hydride, right? That's a very powerful base. A base is something that picks up a proton. If you have a negative charge on you, you're probably going to be a base, either strong or weak. And so this would be the base that would be used here, could be used here. And so H- removes an H+ from the alcohol. So you get a molecule of hydrogen. And this O- is now ionically associated with the sodium. And now maybe we would want to kick in an alkyl halide. So maybe something like this, benzyl bromide. And so the O- attacks the carbon that bears the halide. The halide gets kicked out. And this would be a way of making this ether, right? So this is just a general way of making all kinds of different ethers. But Williamson ether synthesis has limitations, which we'll talk about in a second. Let me give you another example here, is that we could use phenol. And now phenol, as we said, although it looks like an alcohol, it's a special kind of alcohol in that it's a much stronger acid than alcohol is. So here we can get away with using a weaker base. So we could use hydroxide. That's what you're using in this experiment, but there are bases that are even weaker than that. One of them could be sodium carbonate, right? Or sodium bicarbonate or something like that. This is a weak base. Why can we use a weak base here? Because when the OH group is bonded to an arene, it's a much stronger acid than when it isn't bonded to an arene. So here we would get deprotonation of that phenoxide. And now maybe let's kick in an alkyl halide, maybe something like this. And the O minus comes in here to the carbon that bears the Cl. It's going to kick out the Cl and take its place. So this would be a way of making this ether. And you know, this reaction, making ethers, this guy here, I don't know if you've ever heard of a wallflower. Yes, a wallflower is someone who stands by the wall at the big dance, and they never make it out to the dance floor because they're shy or embarrassed or whatever. But there actually is a plant called a wallflower, and this is its aroma. So this Williamson ether synthesis is used a lot in the perfumery and personal care industry because many of these ethers have some very nice smells, and they are volatile, so they can be perceived by others. Okay, so the synthesis of nerolin, it's just a specific case of this Williamson ether synthesis, where you have, it's a two-step reaction. You have an alcohol or phenol, you hit it with base, and then you throw in an alkyl halide. But Williamson ether synthesis has limitations. So I want to talk about that for a second. Limitations of Williamson. And one of the most important limitations of the Williamson ether synthesis is that the alcohol cannot be tertiary. Why? The O minus is too crowded. Right? So if you can imagine an alcohol such as this, right? That's a tertiary alcohol. And now I'm going to make it an extreme situation. This wouldn't work, but now I can make it even more extreme and go medieval on this thing, right? And now I've made this a very sterically crowded tertiary ion. When I add sodium hydride, that's the base to this thing, this O minus is now in an extremely crowded environment surrounded by these three fishtails, right? So the O minus now is too crowded to get in there to remove the halide from the alkyl halide. The O minus is now surrounded by all of these fishtails. The O minus has to make contact with this carbon, but being surrounded by all these fishtails are going to make it impossible for that O minus to get in there. So the alcohol in the Williamson ether synthesis cannot be tertiary. The reaction will not work. But these two guys aren't just going to sit there doing nothing because they can't do a Williamson. Oh no, they're going to do something, all right. And what they're going to do is another kind of reaction called an elimination reaction. So all of this crowded environment has denied to this O minus the ability to kick out this halide. But it's not just going to sit there doing nothing because it's a base, right? This is a base. A base is something that removes protons. If you have a negative charge on you, you're going to remove, you want to remove protons, you're going to be a base because a proton is H plus. So when the alcohol is tertiary, when the alcohol is crowded, instead of doing a Williamson, let's call the carbon that has this halide, we'll call him the alpha carbon, the carbon next door to the alpha carbon, let's call him the beta carbon. When the alcohol is tertiary, what is going to happen is that the O minus is going to remove this proton on the beta carbon, that's the carbon next to the carbon that has the leaving group, that has that X, the thing that leaves. These electrons rush in here to make a new carbon-carbon double bond, and the electron-greedy halogen takes off anyway. See that arrow going from the alpha carbon to the X? Well, we've seen that arrow before plenty of times, right? We've seen that arrow before plenty of times. You just saw it over here. This halide is greedy for electrons. This bond is going to snap because the halide wants those electrons. And so what we get here is the original alcohol back again, now with that proton restored, plus an alkene plus X minus. Right, so this Williamson ether synthesis has this limitation, is that you can't junk up the O minus formed in the first step. You can't junk it up in a sterically hindered, sterically crowded environment because you won't get a Williamson reaction. You'll get an elimination reaction. This will be a side reaction. Maybe you don't want this alkene. So that's one of the limitations of the Williamson ether synthesis. I don't want you to think that any old alcohol will do. Another limitation is that the alkyl halide that is used in the second step, the alkyl halide in the second step, this has to be primary, because if it's anything else, it's going to be in a too sterically hindered environment. So that the Rx must be primary. It cannot be secondary or tertiary, because if it is, an elimination reaction will happen. Or else we get elimination as well. Okay, so now I'm going to make this alcohol super primary, right? There's no problems with methanol, so this is as sterically unhindered as an alcohol can get. I'm going to add a base, let's say sodium hydride. I'm not using hydroxide because it's not a strong enough base. And so that O minus is not in a crowded environment, that's fine. But now what I'm going to do is I'm going to really junk up the environment of the alkyl halide, right? I've made that alkyl halide tertiary. I've put it in an extremely crowded environment. And now the O minus can't get in there to kick out the X. It's just too crowded. But once again, these two guys don't sit there doing nothing. We get an elimination reaction. How does elimination work? Call the carbon that has the halogen, call him the alpha carbon. Call the carbon next to the alpha carbon, call him the beta carbon. So in an elimination reaction, which is what happens when a Williamson goes bad, the base removes the proton on the beta carbon. These electrons rush in here to make a new double bond, and the X leaves. So the products here would be the starting alcohol with the proton restored, plus an alkene. There's my new carbon-carbon double bond, plus X minus, which will be chloride or bromide or whatever. So just because we have a general recipe for the Williamson doesn't mean it works in every situation, and the alcohol can be anything and the alkyl halide can be anything, right? And it turns out that even if the alkyl halide is secondary, that's just too crowded for the for this alkoxide, for this O minus species to get in there. Okay. Let's talk about the NMR and the IR of nerolin. Nerolin, NMR. How many signals? Okay, anyone want to take a shot? How many signals are you going to get from nerolin? How many signals? Anyone want to give it a go? No, no takers out there? Aha, I see the right answer. 9 signals. All right, so this is going to give you 9 signals. Okay, so how did I come up with that? Well, there's 1, HA. There's 2, there's 3, there's 4, right? This molecule, what is its one and only symmetry element? A plane of symmetry, which is the plane of the paper. It says the top of this molecule is the mirror image of the bottom of the molecule, but there is no symmetry element that says HA is equivalent to HD, or that B or C are equivalent, or that HE is not related to any other symmetry, is not related to any other proton, nor is HF, nor is HG. Okay, and then we have this ethyl group here. We have HH, and then we have the 3 HIs there. So I got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 signals. And furthermore, the signals of this benzene that are on this arene, they're all very similar chemical shift, right? What is it that controls the chemical shift? How close you are to a multiple bond and how close you are to an electronegative atom. Well, all of these guys are, they're not in the same chemical environment, but these guys over here, they're very far away from this oxygen, and they're all about equally far away from a multiple bond. So what you're going to see in the NMR of nerolin is a mess between about 7 and 9 ppm. You're going to have 9 signals, right? And what will the splitting of those signals be? Well, this guy is going to be a doublet. What about HB? What's his splitting going to be? Oh, he's going to be a doublet of doublets because he's split by the HA and the HC. And that's going to be a doublet of doublets. And that's going to be a doublet. So it's going to be a big mess in the arene region of the NMR between 7 and 9 ppm. Okay, however, this guy is going to be very nice and clean. What is his splitting pattern going to be? Tell me in the chat. What is the splitting pattern of the HH going to be? Yep, it's going to be a quartet. And what about the splitting pattern of the methyl group? What's that going to be? That's going to be a triplet. So the nerolin NMR, and who's going to be more downfield, the quartet or the triplet? Or who's going to be more upfield? Who's going to be more upfield, the quartet or the triplet? Most upfield signal, is it going to be a quartet or a triplet? It's going to be an upfield triplet. So the NMR of this guy is going to look like this: a mess, a mess, a mess. 9 signals, a bunch of doublets, and other stuff. It's going to be a mess, but up here, you're going to have a very nice quartet. And then you're going to have a nice triplet up there, right? So the NMR is going to look something like that. Okay, let's talk about the IR of nerolin, right? And we get this mess here because all of the chemical shifts of all of these protons are all about the same, and the splitting patterns are complicated, and we have a lot of them. So in this experiment, so one of the takeaways of this experiment is that NMR, you don't always get these nice singlets, doublets, triplets, quartets. Some molecules, and nerolin is one of them, doesn't have the good taste to separate out all its signals so they're easy for us to interpret. They all get bunched up, they all get distorted, it makes an ugly, ugly mess. It's not always singlets and doublets and triplets all beautifully separated one from the other. It's one of the challenges of NMR. These guys, a mess between 7 and 9 ppm. Okay, let's talk about the IR of nerolin. What are we expecting to see? Well, IR is telling us about the functional groups. So one of the functional groups that I see here is carbon, yeah, is carbon-carbon double bond stretching of an arene. So we're expecting to see something that says, oh, we're looking at an arene. And where is that going to be? At around 1600 and maybe another peak at about 1500 wave numbers. Okay, so what else are we expecting to see in the IR? Right, we have a benzene ring in there. We're going to see a peak that is due to the benzene ring. Another thing we're expecting to see is the stretch that is due to a hydrogen bonded to a benzene ring carbon. So we're expecting to see sp2 carbon hydrogen stretching. And there's a hydrogen bonded to an sp2 hybridized carbon. So we're going to see those. And that peak is at around 3050 in the IR. So if you have some nattling and noodling above 3,000, but close to 3,000, that's what you're looking at. You're also going to see sp3 carbon hydrogen stretching at around 2950. And then maybe carbon oxygen stretching, and that's way down here at around 1200 wave numbers. So the IR of nerolin is not really that informative, because when you look at the IR, and I'm pretty sure that the teaching fellows will show you both the NMR and the IR of nerolin. The IR of nerolin, well, it's not really that informative. You can make out that you have a benzene ring in there somewhere, but all of these other peaks are going to be swamped by a bunch of other peaks as well. Okay, so that's all I have for you today. Remember, next week we have the lab quiz, and I'll be publishing a study guide for that, so you can bone up on that. All right, so